Hello and welcome back to the Oxford MAT Livestream, or if you're joining us for the first time, welcome to the Oxford MAT Livestream. This is the show where we go through the syllabus for the Maths Admissions Test, revise some A-level maths, talk about some problems, do some revision and warm-up, eventually try some math questions as well for anybody who's getting ready for maths at university. I'm doing a kind of intro because I've met lots of people at the open days recently, so I think lots of people maybe are finding us for the first time. Don't worry about catching up or trying to see everything we've previously done. We've got videos that are not going anywhere. If you want to see things from previous worksheets or previous bits of content, so far we've covered algebra, polynomials, and a little bit of integration and differentiation. Today we're going to look at the graphs and transformations parts of the MAT syllabus. So hi everyone in chat, including some people who I've met at the open days over the last couple of days. It's been really nice to run the open days here in Oxford and meet people. It reminds me that people in chat are also people I could one day meet somewhere, and at the moment we've got people who so far names start with A in chat. We've got Anonymous, Anusha, Aya and Andre, and more anonymous people. Hi everyone. You can be anonymous in Slido chat if you want to join in with that. There's a link on the Matt Live page or in the YouTube description, or if you go to slido.com and put in the event code MATLIVE, you can join in the live chat that's running now, which is also where you can take part in polls such as this one for how was your day today, to let me know how was your day today. While you're voting, solid 3 stars straight away there. There you go. Middle of the road. Let's see if we can improve that with some graphs and see if we can apply a transformation. F of x minus 2. Right, okay. While you're doing that, I've had a request in chat from somebody who was at the open day where I mentioned an interview question. We're going to do a special episode on interview problems in November as we get closer to that stage of the Oxford admissions process. They've asked me for suggestions of how to do the question. Fair enough. So what I've got is the setup here. I've got 3 points on the parabola y equals x squared. A and C are fixed and B is somewhere in between. I'd like to make the area of ABC really large because, of course, if B is really close to A, then the triangle is very skinny. And if B is right over here, then the triangle is very small as well. But somewhere in the middle, like maybe around here, the triangle is nice and large in terms of area. And their question was, how do you do this question? How do you make progress? Really, I suppose I should say I'd like people to try and think about this and come up with different ways. The reason it's hard is that you know lots of different formulas for the area of a triangle. And in an interview, I would try and get people to think about what changes when you move B and what stays the same. So that maybe people could spot that something that stays the same is that this line AC, excuse me, there it is, this line AC stays the same as you move the point B. So yeah, suggestions in chat are coming in. Syrup suggests that we go for an isosceles triangle, which I suppose might be quite large. And that lets me interrogate as well. In an interview, I'd ask back why you picked an isosceles triangle. Anyway, I was saying this side stays the same as you move point B around over here, which means that this side over here is fixed. And it actually makes sense, I think, to call this the base of the triangle. I know it's on the top, but if you turn your head round, then that could be the base of the triangle. And then the question is to maximize the height, or the perpendicular height. And this happens at quite a funny point because these points are on a parabola, so B moves further away from the line in a complicated way as it moves around. This is quite a nice idea, especially if I mark in this line to say, what I really like is for this point to be as far away as possible from that line. And if it's as far away as possible, then instead of being around here somewhere near A or C, where the height is not very much, I should move it as far away as possible, which happens when the tangent is parallel to that line over there. So if this is the normal, this is the tangent, then it's sort of, you can't get further away from the line than that. So it turns out that I would like the tangent to have the same gradient as the line between A and C. Anyway, small diversion, nothing to do with graphs and transformations really, just something that I mentioned today, didn't tell people the answer to, and maybe there's one way to do the question. There are other ways, of course. You could give all the points names, which I suppose you'll probably do at some point anyway, A and C are fixed, but then B is the thing that's changing. So you could kind of write down the area in terms of knowing maybe a formula for the area. And whichever formula you pick, it will depend on B. Maybe if you try really hard, you might be able to differentiate that with respect to B. That method is quite difficult depending on which formula you pick for the area. If you use a formula that explicitly uses the fact that AC is fixed, then you stand a better chance of doing it that way. So it's weird, actually, because it's a bit wonky. This point is not the midpoint of AC, and these lines are not the same length, AB and BC, in the final answer. So it's not isosceles, sort of scaling triangle in the end. So it's maybe not the triangle you might expect. Something to think about there. Okay, right. Thanks for voting in the Amateur Today poll. I think 4 stars there's one, and the average score there is 4.2, so that's all very nice to see. Let's have a look at chat again. There we go. Okay, my plan is to do graphs and transformations today. So to get on with that, I would like to have a look at the MAT syllabus first. This is a list of topics taken from AS level mathematics that we think people will learn by the date of maths. Whether or not you're doing AS levels, maybe you're doing something else that's equivalent to AS levels, we think that you'll learn about graphs of these functions at the top. I've got pictures of what they look like in a moment. And we think that you'll learn about some basic transformations, some stretches, and some translations left and right and up and down, moving by a constant amount A, which maybe you're moving left or right along the x-axis, or maybe you're moving parallel to the y-axis to transform that graph. Okay, let's jump in with revision notes then. I'm going to switch chat off the screen just so I've got more space. I can still see what's going on here. For example, someone in chat has just said, "Hi James, what have I missed?" They have missed a bit of an interview question, but we're just about to launch into revision for graphs and transformations. Okay. And Syrup wants to ask about a question from a previous sheet. There is a suggestion of how to do that question, Syrup, in the solutions document as well. I've made a solutions document partly because we don't have time to talk about every single problem in the live show. And there's a little bit of description in there. If you find the solutions on the MAT Live webpage and scroll down, eventually there's a bit about the extension problem. That's next week. That's logarithms. That's next week, Syrup. Syrup, that's next week. Okay, right. So graph is all the points in the xy plane that satisfy the equation. So it shows, I guess, the value of f of x if you're doing y equals f of x. But you might like to think about when you draw a circle for something like x squared plus y squared equals 1, you're showing me all of the points in the xy plane that happen to satisfy that equation. Maybe that's not how you think about it at all, because you're thinking about drawing a line rather than drawing lots of points, but I suppose a line is made of lots of points. Welcome to the MAT Livestream. Sometimes I say things that sound clever in my head, but aren't actually very clever. Here's some pictures of quadratics. For a quadratic, it's the leading coefficient, the bit A, the ax squared at the front. A is the number that determines whether your quadratic curves upwards or curves downwards. That affects the picture, it affects the behaviour for large x, it affects lots of things about the quadratic. Andrea in chat asks about whether you need to describe transformations with vectors, and the answer is no. Describing them in words is fine. We will normally describe them in words as well if we were asking a question about them. Cubics are polynomials of degree 3. Because it's a polynomial of degree 3, its derivative is a polynomial of degree 2, a quadratic, so it might have 2 turning points. I've given you examples there with 2 turning points on the right, 1 stationary point on the curve in the middle, and the thing on the left has got no stationary points at all. Good. I've said 0 or 1 or 2 turning points in the notes. That's not quite true, is it? That's not a turning point on the one in the middle. I should change that. I mean stationary points for this. We just had the differentiation live stream last week where I made a big deal about the difference between a stationary point versus a turning point where it actually comes back again. Oops. Okay. And then advice about higher degree polynomials. Sketching polynomials is the sort of thing that we practiced back on the polynomial sheet. I've got a picture here of cos and sine and tan. It's not my best picture of tan, I think. I've really zoomed in to show you sine and cos. Varying like that. Tan, of course, gets very large, near 90 degrees, because being sine over cos, as cos gets close to 0, that fraction gets very large. And then I've got assorted more graphs. You've probably seen this before, but I just want to show them to you again. Square root x on the left there is very steep near the origin. A to the x might look like an increasing exponential or a decreasing exponential, depending on how large a is. So whether you're shooting off larger and larger, faster and faster, or whether you're decaying down slower and slower. You might have seen things like e to the x or e to the minus x, and in a sense that's pretty much what I've drawn in those two pictures. And if you've seen exponentials, then maybe you've seen the inverse of exponentials as well. Maybe you've seen logarithms. The graph of log x looks like this. It gets very negative as you get close to 0, and perhaps you know that you shouldn't put 0 into a logarithm. For small positive numbers, the logarithm there is a very negative number. I suppose log base 10 of 10 to the minus 6 is minus 6. So it's a very, very negative number, minus 6. If I put in that tiny number, 10 to the minus 6. Maybe I'm thinking in scientific notation for those numbers. Okay, it grows. The rate of growth slows as it goes from left to right there, passing through important feature points like crossing the x-axis when x is 1. These are things that you know, I think, from laws of logarithms, you know, kind of algebra and maybe numerical numbers for numerical numbers. You know some numerical facts about the logarithm function. You can also put them on the graph there when you're drawing these. Just some words about transformations. I think for the benefit of the person who asked about how to describe transformations, I've tried to be precise with my language in the notes there for this bit. We've got graphs. That's the beauty of saying I'm being precise with my language and then immediately turn around and say I've got a giraffe that I'm transforming. Goodness me. It's been a very long day with open days as well. Giraffes everywhere. Right, okay. So you're translating your graph maybe by distance a in the positive x direction. I think that's technically how I would personally describe it. For the graph of f of x minus a, and people might say if a is a sort of known number like 1 or 3 or something, then people might say 3 units to the right or 3 units in the x direction. Just to be super clear on here, I've positive x direction, so you know I mean that side of the x-axis. Okay. Just head off. I seem to be still doing open day, which is fine, of course. It is still the open day. There's an open day question in chat. Somebody's asked, if I do an EPQ, should it be about maths? And the answer is, you can do an EPQ on anything you can do an EPQ on. It might be something you can talk about in your personal statement, but Oxford doesn't use it for standard conditional offers. We are unlikely to ask you to get a particular grade in it, and we don't have any requirements about doing an EPQ. So if you can do one in maths, that sounds fun, but I know lots of people can't do them in maths. They can't do them, don't have that opportunity. But it still might be fun as a thing to do anyway. Goodness me. Right, okay. That's all I need to know about graphs and transformations, I think. We've got these ideas about maybe transforming some of these graphs. You saw on screen there, Andre in chat has got this idea about what happens when you translate the logarithm graph, because you have laws of logarithms that you could start to bring in on this. And we've got up here somewhere pictures of square roots and exponentials. I mentioned there something to do with e to the minus x. Let's do a quick bit of algebra. So I try and link this to exponentials and power laws. E to the minus x is an example that looks like the thing on the right. But hang on, the thing on the right says 0 less than a less than 1. So what's going on there? What's the link? And the link between this and a to the x with 0 less than a less than 1, looking like this, looking the same. These have got pretty similar graphs because this thing is e to the minus 1 to the x, that's a power law, and then I can write that as 1 over e to the power of x. If I can write the letter e. This thing in the brackets here, 1 over e is between 0 and 1, so maybe that's why this is an example of a graph like the one on the right, where it's decaying down like that. So if you saw that and thought that looks like an exponential, decaying exponential, then yes, a decaying exponential is an example of something like that. I suppose even better if I change if I change this to look like e to the minus kx, then we're cooking, because then this is e to the minus k to the x. And this could be anything, I think. E to the minus k, anything between 0 and 1, right? If k is some positive number. This could even be sort of 1/2, right? E to the minus k could be 1/2 if, and then k is something like natural log of 2. I've tried to do that too fast. I regret doing that too fast at 5 PM after an open day. Log both sides, minus k is minus log 2, k is log 2. Good. Woof. I've had a few horror shows with minus signs on the Matt live stream so far, but that's not one of them. Touch wood. Right, okay. Good, just trying to playing around with these ideas, trying to link things together. We've got a lot of exponentials and power things to go on here. That square root on the left. I know from the algebra stream that some people already know this fact, but if you have y equals root x, then it's true that, this implies if this, then y squared is x, which looks a lot like the parabolas that you learn about. They say y equals x squared, and this says y squared equals x. So they're kind of switched around x and y. This is a parabola, y equals x squared, but this thing, y squared equals x, is also a parabola around this way. Y squared equals x is this one. It's been reflected to switch around x and y. I'm not sure you need to know that. You might be perfectly good at drawing square root x without thinking, yes, I'm drawing the left side of a parabola reflected around so that it's now the top half of a sideways parabola. I'm not certain that knowing the words helps you draw the graph, but these things are connected, so it's worth talking about the connections. And just because this is close to home, suggestion in chat, someone asks for advice watching the live stream with autism and ADHD if you find hard to pay attention. We're recording this, and even during the live stream, YouTube lets you pause a live stream so that if you want to pause and go and do something different. I have to go at the speed of kind of how chat wants to take things and how the group of everyone I'm teaching at once wants to take things. But you have power over me to pause me, rewind me, or if you're watching the replay, fast forward me. So I think that's a way I can accommodate this. If you're not into the videos, then the worksheets and the solution sheets should work as a standalone resource. So that if watching a video and having a chat about the problems isn't really your style, you can ignore me entirely and you're not missing out, because we've got the solution worksheets as well. The solution sheets have got everything that you need to get the answers to the questions. Good, okay. Trying to accommodate everyone. One of the reasons I like YouTube is that they let you do stuff like pause and rewind. You can pause the live content, you can rewind the live content. You can't yet fast forward live content because I haven't said it yet. But one day YouTube will work out that technology as well. And you can, I'm sure one day you'll be able to fast forward to see what I'm going to say next. And then you can let me know in chat. Right, okay, we've gone to a weird space. Let's bring it back. I've got some revision questions. Here are some revision questions. I have got on the page at the top there, this is just the question sheet from the Matt Livestream page. I've got 15 of them. And I don't really want to talk about all 15 of them for the next half an hour. I'd have to talk about them quite fast. So what I'd like is suggestions in chat about particular questions that I should focus on. If you're seeing them for the first time now, I'm going to scroll through them a little bit, so that you can have a look at what's going on and have a think. Looking to next week when we talk about logarithms, I've got another one of these coming up next week. So if you want to get ahead, then you can see the worksheet on the Matt Livestream page if you would like to form an opinion before I've even started the show. Okay, we've got some curve sketching here and some ideas about doing transformations and whether that gives you the same graph or not. 3 and 4 and even 5 really are just getting you to sketch particular graphs and do particular things. I've got a weird graph there, sine of x squared, which is a bit of a classic, and square root x squared is also quite fun. 8 is very standard sort of stuff, and further down I've got transformations again, 10 is a little bit tricksy. It's a little bit silly, really. And then 11 and 12 go together, and the last 3 go together. 15 is extremely difficult. I used this question last year, and I'm not ashamed to say that this year, when I got the worksheet out, I could not remember how to do question 15. I think I may have written that one to be too hard. I've written a question that I can't do. Question there about, do I recommend doing the step as well as maths? If you've learnt the maths for step, then you might like that as a source of tricky questions. If we're talking about Oxford admissions, then you don't need to do step. Kiba asks about, let's do this first. Kiba says, what does sketch all the points even mean? And this is me asking you to draw, all of the points, which might form a line in the plane, or maybe a circle, or maybe something else, to draw all of the points, which is what you're always doing when you do curve sketching. It's this idea that when you sketch y equals f of x, what you're really doing is showing me all the points x, y, all the points in the xy plane that satisfy this equation. And because it's a function f, there's only one for each value of x. So you draw something like this. But you also know how to draw things like this, where that's not a function, y function of x. This is just a collection of points that all satisfy this equation. So for 13, 14, 15, I've tried to phrase the question so that I'm not saying it's a function, I'm just saying there's some points in the plane that do this. We might just rearrange this and see if we can algebraically spot what's going on for each of those. I think they're too hard as well. When you sketch the graphs, what do you need to label? Well, I think life advice, it's probably a good idea to label points where it meets the axes. It's probably a good idea to think about points where 2 graphs intersect if you have 2 graphs. But for the mat, this year you're not going to draw any graphs and you're not going to label any points. So I think it's a good skill to have to be able to sketch these things and to draw them. It's not something that you're going to be doing in the actual mat. Right, good. Okay, but I'm doing revision on it anyway, because sketching graphs can help you reveal things about the equations, which hopefully I can reveal on 13. It forces you to think about where these points are. Good, okay. 12, how do you do 12? And why is there a weird ellipse in it? Yeah, it's good, isn't it? Okay, so there are some requests for 15. I saw question 1, the last part, 5, and then 11 and 12. Okay, so I think there's some requests to do a couple of early bits. So a couple of early bits. I'll do a bit of question 1, we'll do a bit of question 5, and then I saw, was there 9 in there? Did I imagine that? I think I imagined 9. And then, yeah, pretty much 11, 12 and onwards. So let me just lay this out of what we're going to do, 12, 13, and then probably people just want me to do the things at the end where I think I may have got a little bit carried away with the question writing. Nah, they're fun to write. Quite not so fun to do when you remember it's time to do graphs again. Okay, so question 1. Gives you a pair of transformations and asks you to do one and then the other, and these do not end up being the same thing. It's just not the case that 3 times f of 2x is the same as 2 times f of 3x. They could be the same though. So this last part which somebody's asked me about is to show that essentially it could be the case that those things are equal. The numbers have changed to 5 and 4, but still. When you have an equation like this, it's pretty impossible to actually solve this, right? To do any sequence of logical steps where you maybe transform this and get to some sort of solution. You're not going to square both sides, divide by 4. It's not going to help, right? It's going to be numbers in all the same places. So although you don't have any techniques to solve this in general, you might be able to find an example just by trying simple functions. A bit like in polynomials, when you're looking for solutions to an equation, you might have a technique like the quadratic equation. that helps you find solutions. We might just try checking numbers to see if they work or not. So different ideas there for different approaches. Anyway, so I'd try a simple function. I might try, well, what's simplest? I suppose I might try g of x being some sort of constant. And if g of x is just a constant, then this one says, what's g of 4x? Well, it's still just constant, isn't it? 5c equals 4c. So this works if 5c is equal to 4c. So, doesn't look very likely. So maybe works if c equals 0. That's a pretty boring function, though. I mean, this works. So if g of x is 0 for all x, then good. This works. Everything's okay. Both sides are equal. You asked me to make the y equals 5 times g of 4x and 4 times g of 5x have the same graph. Here's the graph. Deadline. 0 everywhere. Terrible. So an anonymous person in chat got there just at the same time as me. Fantastic stuff. Yeah, not very exciting. Don't love it. Can we do better than that? Is there a more interesting example? It's not in the question. It doesn't say find a second example. How would I word that? In brackets. If your first example is really boring, please find a second example. How do you write that question? But maybe curious mathematicians who might think, is there another solution? Can I do something else? Can I do something different? Yeah, and there's solutions in there to try, solutions coming through in chat to try g of x being maybe a times x plus b next. I think that's what I would try next. And maybe this works, maybe this doesn't. In fact, if I plug this in, then it turns out that I want a to be anything, but b has got to be 0. I think g of 0 has to be 0 because plugging in x equals 0 up here says, if this is going to be true for all x, then it's going to be true when x is 0. So a non-trivial solution, g of x equals ax works. That's an example where I tried something that was slightly too complicated and it didn't work, but then it does contain this large collection of non-trivial things. Yeah, Andrew's saying, is there a non-trivial solution? Which is a good way to say it. Ooh, g of x equals mod x. I think that works, yeah, that does work because they're both 20 mod x. Yeah, that's nice. I like that a lot. Can you do something weird like 3x if x is positive, 2x if x is negative? You know, different gradients on different sides. I reckon you probably can. It's linear, right? Maybe? No, maybe not. Okay, whatever. Other examples exist. Let's skip on. Question 2 plays a similar game to do these transformations and to talk about whether they commute or not, whether they can change the order of operation, and again, you're asked to find an example. Again, I would try simple functions. In this case, setting g of x to be just 0 function doesn't work because that left-hand side would be 2. The right-hand side would be 0 for all values of x. So we've got to think a little bit harder. Maybe there's some form of x plus b, a linear function that works in question 2 as well. Okay, I'm skipping that one though because nobody asked for it. Question 5 is about sketching logarithms. And hey, we're going to have some logarithms at some point later in life. Next week is logarithm week. Let's talk about question 5. It starts by asking for the graph of log x, which we already looked at. Is it log base 2x? I've just lost it. There it is, yep, log base 2x. And then it asks for y equals log base 2 of x squared minus 2x plus 1. So something we might think when we see that is, well, when x squared is large, this expression is going to be large, so I expect this to end up at a large value. And when x gets close to 0, oh, this is log of 1, which is 0, so this goes through the origin. And maybe I can find some other points on there as well. But maybe you spotted that this is closely related to the graph of log x. And because the polynomial inside, you've seen this before, I think, x squared minus 2x plus 1. I reckon you've probably seen it. Yeah. There's an anonymous person in chat, and they put question marks on their post, but it's spot on. So confidence, please, confidence. I know confidence doesn't work like that, but you can't just have someone on the internet say confidence, and then you're confident. But one of the reasons that we let people be anonymous is so that you can just say stuff. And if it's not true, then no one even knows it's you. Right, okay. Is it worth me reminding people that nothing you say in chat has anything to do with admissions? It's not linked to any Oxford application you might make. We don't try and work out who's who, even if you are using your real name, because we have no mechanism to know whether you're using your real name, and it would be mad to try and base anything on this. Yeah. Okay, so there's 2 times log base 2 of x minus 1, which is a translation and a stretch. So it translates left by 1 unit. See, that's me being a bit more casual with language. 1 unit in the negative x direction parallel to the x-axis or something. Everything gets doubled. So essentially it's a combination of a translation and a stretch. Good. Okay. What have I done? What have I done? Oh, I've done it wrong, haven't I? I've translated the wrong way. It's a minus sign error. Welcome back to Oxford MAT Livestream, where I can't get the signs right because it translated that way. Excellent stuff. So that when x is 1, this has gone very, very negative. Good. Never get the minus signs right. Why would it move to the left? Oh, everyone in chat. Oh, everyone in chat is right and I am wrong. I made it half an hour this time. Half an hour into the live stream before having a clanger of a minus sign error. Everyone in chat, give yourself a little pat on the back. You translate it right when there's a minus 1. Okay. So this thing is not defined when x is equal to 1. 1 minus 2 plus 1. Yeah, it'll be log of 0, which you should probably not do. So what's this point over here then? The answer is that over here, this is 2 times log base 2 of mod x minus 1. The absolute value of x minus 1. There's something subtle going on with squares and square roots, right? When I pulled out this factor of 2, I was kind of writing down the square root inside here of something that should be positive to be fed into my logarithm. But algebraically it's true. But in terms of actually having a defined value, this is only true if x is bigger than 1. And if x is less than 1, then I should have written this as 1 minus x squared, which is algebraically it's equal to. And then brought out the factor of 2. I went too fast. So why the mod? It's because log base 2, or whatever, of x minus 1 squared is equal to log base 2 of 1 minus x squared. So these things are true. These are both fine, because we're taking log base 2 of a positive quantity. But then these things, which I want to write down in the next line, these are not really equal, in a way, because the one on the left is only defined when x is larger than 1, and the one on the right is only defined when x is less than 1. So this is a bit strange. We have this situation where on the right of x equals 1, we get some translated logarithm, and on the left, we're going to translate it and reflected thing with this 1 minus x in it, like this. I see why somebody asked for this question now, because they fast forwarded in time and they knew that I would have trouble with it. So I see you, time traveller, who's come in and asked what's going on. Yeah, so it's like a bit of a subtlety that you might have 3 minus 2 squared is equal to 2 minus 3 squared. It's kind of like the same idea, right? 3 minus 2 squared is equal to 2 minus 3 squared, but it's not kind of okay to get rid of the squares. You run into all sorts of trouble. And one of these, depending on the value of x, one of these is getting by on a negative number squared, where you should be really careful if you want to rewrite that in terms of a logarithm. I was not careful enough, which is why I got my minus signs mixed up, because then I tried to join the dots. Good. Right. Yes. Okay, and there's some standard questions about translations, and people have got me to skip the standard looking questions. Look, I reckon I probably could draw sine of x squared now. Yeah. Are you allowed to just stick a mod in there? Okay, so I'm not really just sticking a mod in there. I'm thinking very carefully now that I've caught myself. Thank you, chat. So I would say that this thing is equal to this if x is bigger than 1. Then these things are equal. And I'd say it's equal to this if x is less than 1. And that's to do with careful consideration of which way round, where these logarithms are defined. So I have these two cases. And then a snappy way to write that is to say, aha, this is just the absolute value of x minus 1 in both cases. Because on the right there's a minus sign, but absolute value, modulus sign stuff, doesn't worry about that minus sign. That is subtle. I think I missed this last year as well. What's this in chat about sine of x squared? Oh, sine of x squared is confusing. Okay. Right. Last part of question 1, sorry, we had a go at this. Not just now. Last part of question 1, we tried some simple functions, like a constant function, or like a linear function, and we found out that a times x works for any value of a. So that's a thing we just played with up here. Okay. Sine of x squared is quite fun, so I would like to have a go at sketching it. It's not a standard transformation or anything, it's just an interesting graph. It works like this. When x is 0, you get sine of 0. As x increases, then of course, well, you're putting increasing values into your sine function, so you're going to see some sine stuff. But as you go through, x squared gets larger faster and faster, which means that your graph is going to go between -1 and 1 faster and faster as the value of x squared absolutely shoots up past 360, past 720, in no time at all. It gets all the way up to 3,600, where the poor sine wave has to go through 10 oscillations as you go through. If you prefer, then sine x squared is equal to 0 is something that you can work with. You could say that, well, I know when that happens. When does? That's something you could think about, and you'll find that those points get closer and closer together as you move to the right. Okay, that's question 6, just interrupting my sequence. But that's okay, because I like drawing sine. So I should draw the negative bit as well for negative x, which would be kind of the same but upside down. Let's just put it over there. This is going to test my ability to draw something symmetric. Lovely. Perfect. Art stream. Right. Yeah, sine of 1 over x is also cool, says someone in chat, and they're correct. Sine of 1 over x. When we ask people to sketch graphs, in the MAT, we have switched since 2018 to only ask questions using degrees. This is because we think some people haven't seen radians yet. If you've only seen degrees so far, don't worry. We're only going to mention degrees in the MAT. Later in life, you might learn about radians, which I think are better. But that's my ability. Oh, is it a second clang? It is a second clang. I might be too tired for this. X squared, people have reminded me that x squared, when you put negative numbers in, you get the same answers out. So really I should have drawn the same thing over this side, reflected on this side. That's 2, but they're coming faster and faster. Like sine x squared, my minor sign errors are getting closer and closer together until we get to the end of the live stream, and I'm going to be making minor sign errors just constantly. Oh my goodness. Whoops. Yeah, the pattern reverses. Sine of root x. Sine of root x is the other way around. The zeros get further and further apart, kind of because those root x things will be need to be a multiple of 180 or 360 degrees or something. Let's see. Can I show you this? Is this something I can draw? Yeah, maybe we could quickly play with graphs on Desmos. I do like Desmos. So if I switch to Desmos quickly, there we go. What can I do over here? I can do a function like x squared. and then I can do sine of f of x. You can see, oh yeah, symmetric left and right. That's nice. Oh, it's very similar to that parabola, isn't it? That's kind of cool. But then we could put in root x instead, and yeah, I guess that's only divided on the right hand side. And this has zeros that get further and further apart. Look, there it goes, all the way over there. I think my Desmos is using radians at the moment, but not very much changes if I switch it to degrees. Except everything I have to go to. Oh, well, okay. It's much harder to see in degrees, isn't it? Because I've got to zoom this axis out so that we can see 360. But really, I only want this one to go to 1. And that follows a little moment. There we go. Is that a bit better? It's a bit better. Oh, it's still taking forever. Up and then down again. Because they're getting further apart. So anyway, that's going to take ages. Right, good. Some questions are easier to ask in radians because radians are nicer, but personal preference. Okay, right, okay. I'm making so many minus sign errors, but I'm going to do my best. Let's see if I can get through 11, 12, 13, 14, 15. I think I'm going to do about 20 minutes on this and switch at 6 o'clock to talking about MAT questions. So if you're watching the replay and you want to skip to some MAT questions, there might be timestamps in the video, there might be timestamps on the timeline, but I reckon it's going to be about 20 minutes. Okay, 11. So this asks for all the points that have cosine x equal to cosine y, which is quite a lot of them. It's quite a lot of them because it includes all the points with x and y equal, of course, because then their cosine values would be equal. But it also includes, because you know some rules about cosine? You know that cosine of a negative number is the same as cosine of that same positive number. So cos x is equal to cos of minus x. So if x and y are negatives of each other, it includes those points as well. That's two different lines. So far my graph looks something like this. Two different lines. But of course there's more in there as well, right? Like y is if y is x plus 360 degrees, which is another line up here somewhere. And there's a few more, like y could be 720 more than x, or it could be 360 less than x. Or it could be a combination of these things. So y could be, let's try and get this right. Where do I look? I think it's 180 minus x. No, it's the other one. Is it 360 minus x? 360 minus x. I'm trying to imagine my cosine graph. Maybe I should draw cosine first, right? Cosine. So if x is over here as a number, so forgetting about axes for a moment, if x is a number over here and y is a number over here, so I'm going to put them both on this axis. I know that looks weird, but if x and y are numbers like this, then they might have the same value of cosine. And that would be the case if x and y add up to 360 degrees. So I might have lines on my real actual plot over here, like minus x plus 360 degrees, which goes through that point as well. So I'm going to get this kind of grid of squares. Go through like this, which is nice. That point should be on the axis, that point should be on the axis, that point should be on the axis. Beautiful. Okay. In general, when you do a question like this with f of x equals f of y, you're thinking about points where, you know, y could be equal to x, or if the function f repeats values, if it repeats the same values, then there could be different points where x and y are different numbers, but which have the same value. Okay. Anusha in chat has asked about 2 to the square root x, which I think sounds very difficult to plot. Let's have a think. 2 to the square root x. So I need x to be positive, so that square root makes sense. I guess this starts out at 2 to the power of 0, which would be 1. And then as root x gets larger, this is going to get larger as well. So there's a tricky question about what's going on near 0, but I think it's going to end up getting larger and larger, right? It's 2 to the x to the half, so it's sort of like this, I think, over here. I think probably like this, but there could be something confusing happening here. quite difficult to decide whether that looks more like root x or if it looks like 2. Looks like the number 1. Tricky question, I like it. If you hadn't said that on the live stream, I might have used that in an interview. I'm not going to do that anymore. Yeah, how would you analyse that? Good times. Exponentials, I guess. Yeah, maybe it's not that weird in the end. Okay, good. What's next? We were doing a little bit of 11, looking at cos x equals cos y, where fx is cos x. Now we've got a different question in 12 where there's a different function. So 2 approaches. Here's the function, and we're looking for points where f of x is equal to f of y for different numbers x and y. So you could think about that in terms of some graph where you have points x and y, and you're thinking, do these points have the same value of f? And there's another one over here, look. So y could be over here somewhere instead. Do they all have the same value? That will give me some points. X comma y would be on my graph, would be part of the solutions of this equation, if f of x and f of y have the same value. There's lots of different cases there because this is a cubic. A totally different approach is algebra, where you could write down the equation that we're trying to solve and try to solve it, which is quite hard. I guess you could rearrange it like this, and that's a bit better because that gives you a couple of cases that you can work with. Then you can break down the problem like that by factorizing and looking at the different cases, which someone says, someone said they found a sort of random ellipse or something, and that's where the ellipse comes from. But I think I like this. So one way to read this is to think about all the possible values that f could take, which, because it's a cubic, is all of the real numbers. If you look at a very negative number down here, then the only possibility, if f of x is down here, is that f of y could take the same value if x and y are equal. So my graph then of f of x equals f of y includes some points where y is equal to x. And for a long time, x should go through the origin, shouldn't it? No, third time lucky, close enough. For a long time, these are the only way for the function f of x to be equal to f of y if x and y are the same number. But then something interesting happens as soon as we get to this value, that suddenly there's a couple of other options, and they're larger values. Instead of being negative, they're positive. So there's a couple of values over here. Doop, doop. Suddenly, at some negative value that we're looking at, it could be the case that x is somewhere over here, very negative over here, and y is somewhere over here. So we have a couple of positive solutions. Okay, and then these continue. And they grow. At some point it goes through the origin, which is when the value is 0, so it's possible that x is 0, or y could be, is that the number 1? Or y could be negative 1. So you can find these intersection points with the axes by thinking about what would happen if x was 0. Well, the function value would be 0, so I should find all the points where f of y is 0, and that's like solving y cubed minus y is equal to 0, which is an equation I can solve. It's got solutions 0, 1 and minus 1. And similarly, you might look for the points where what happens when y is 0, and that tells you a little story that if y is 0, then f of y is 0, so f of x should be 0 as well, and that's that x cubed minus x should be 0, which goes through minus 1, 0 and 1. So you get kind of these points you can join up, and that gives you a different route round to tell this story, maybe that eventually the value gets, if you move to the right, the value gets so large. You're looking at points where y can be equal to x, but there are no other possibilities, and that's if you're up here somewhere for your value, if x is so far over here that there's no other possibility other than y to be equal to x. So it tells you this story about what's going on. So is f of y the reflection in x equals y? I think not quite. So if you're sketching the graph x equals f of y, that's a reflection, but the just function on its own f of y is not a graph, it's just an expression. So we're not quite looking for the points where some graph crosses another graph, right? We're just putting different things into a function. And you're right, there's a transformation here, just off the bottom. There's a transformation here to relate together y equals f of x with x equals f of y, but that's not the intersection of those graphs is not quite the same thing as solving where the equation is equal to something else. So a fun thing to do with Desmos then is to get Desmos to show you different things that can happen when you give it different functions and see how it evaluates to show you different things. Okay, you could do a version. I've done the phrasing in here so that you could just type it into Desmos. Play with that. It's linked to solving equations in a way, to think about when is cos x equal to cos y and when are these functions equal. Right, I've put it off long enough. Let's talk about sketching all of the points that satisfy these things. And these questions are really algebra questions, but they're quite tricky algebra questions. So this first one, x to the 4 plus 2x squared y squared plus y to the 4. When I see that, I'm thinking about x squared plus y squared squared, because that's how you get 2 times x squared y squared, as well as the x to the 4 y to the 4 terms. And then I see the next terms and I think, aha, this is this, isn't it? With another x squared plus y squared. Let's multiply that by minus 3 and plus 2 is equal to 0. So I see this is a quadratic, a hidden quadratic, I suppose, for x squared plus y squared. So that either x squared plus y squared, which I'm now writing as if it's all one symbol. Maybe I should give it a name, but whatever. Minus 2, x squared plus y squared, minus 1 should be equal to 0. So there's 2 possibilities here. Either this bracket is 0 or that bracket is 0. The first one is a circle of radius root 2, and the second one is a circle of radius 1. So this is the equation for 2 circles of different radiuses. So sketching all the points means drawing both circles, which is definitely not a function, because a function would only take 1 value for each value of the input. And this takes like about 4 values for some of the values of the input. I would say an equation for 2 circles. And there it is on the page. If you want the equation for 2 circles at the same time, then off you go. Homework, what's the equation for 3 circles? Can you give me an example? And then this next one down, having said that out loud, I now fear, is that what this one is? Yeah, it might be x squared plus y squared cubed equals 1. Which is not quite the equation of 3 circles, is it? Because, well, I guess it's x squared plus y squared is equal to 1. Yeah. Somebody in chat, and I see now, somebody in chat was asking about complex solutions, because I guess they've seen complex numbers and they know some other solutions to it. But I think once we've seen this, the only real cube root of 1 is 1. That might sound really mysterious to people who haven't seen complex numbers, but this is how I have to talk when I'm talking to people who have seen complex numbers. Let's do another take. Yep, so obviously the only cube root of 1 is 1, so this just means x squared plus y squared is 1. So just a circle, thank you. And then last one, number 15. Circle times a circle. Well, I haven't really multiplied the circles together, right? I've multiplied together these 2 brackets. And if this thing is bracket, so I've got 2 things that multiply to give 0. Either this one's 0 or that one's 0. If x squared plus y squared minus 2 is equal to 0, then that's the equation x squared plus y squared equals 2. And on the other hand, if x squared plus y squared minus 1 equals 0, then x squared plus y squared equals 1. That's a different circle. So there's lots of points that satisfy this equation. Some of them because they have x squared plus y squared equal to 1, and some of them because they have x squared plus y squared equal to 2. And those are both included in the solutions to the original equation. If you like, we factorized the equation, and now we've got these 2 different bits of solution. So question 15. An anonymous person has put it as a question in chat, but I think they're right. The key thing is to factorize this, or to find a way to simplify it, and that's very difficult. My first thought was to pull out xy on the left hand side, but that didn't really help me. And then eventually spot that there are 2 terms with x squared in, and I should put those together. Should I put those together? No. Maybe. What on earth have I done? This is not good, is it? So there's some terms like x cubed. I sort of think that I want to bring these together. X squared, because they've both got a factor of x squared in. Is that what I've done? It's one of those questions where it's very fun to write and then very hard to do. Is this what I've done? I think this is what I've done. Yeah. If you bring together the terms with an x squared in, then you get this. You bring together the y in, you get that. And then those brackets are the same. So this is either y is equal to x squared or x is equal to y squared. So this is a graph for parabola or a weird sideways parabola where I've missed the origin quite badly. Weird sideways parabola for the solutions to those equations. If you like this second one, if you prefer the second one, if you don't like thinking sideways parabola, this is y is plus or minus the square root of x. I think I admitted it before on the stream, but I'm going to admit it again. I forgot how to do this. It's a question that's quite fun to write, because if you're writing these, as a challenge for your friends, you pick two brackets where you can sketch each of the brackets. So you might pick y minus cos x, and you might pick y minus sine of x squared, because we did that one earlier. And then you might multiply those out, rearrange it a bit, try to tidy it up a bit, maybe cancel some terms or something really bad. Then, hey, you've written question 16 on this sheet. Some horrible combination of cos and sine. Homework there, make up your own version of this. The idea being two different brackets, where each of them might be 0, so you get different parts of the graph. Then you multiply them together and you get some horrible expression. I think that question 15 was far too hard. I've got an O in chat from Neutrino. Yeah. Someone answered my question about 3 circles at once. They put a question mark on it as well. But they're right. There we go. Have I got that on screen? Yes. There we go. Third one down. They've shown me an equation for what I believe to be 3 circles of radius 1, root 2, and root 3. All on the same axes, all at once. I haven't tested this, but I think if you put it into Desmos, then Desmos is clever enough to draw the separate circles. Desmos has got some technology for working out when it should join dots together, because it's testing a lot of points, and it's got to know to join the dots up into two circles rather than something weird. If you give Desmos too many circles, I think it gets confused. Homework. Confuse Desmos. Full stop. Okay. That was fun. I feel like I learnt a lot about minus signs and being very careful with symmetries and reflections. And I've learnt a bit about algebra as well. So I feel revised and ready and warmed up to try some actual math questions. Shall we switch to those? Do people want to switch? Let me know if you want to go back and see anything again. But in a minute or so, I'm going to switch to something else. Aya has tried it in chat. Tried it in Desmos, and then tells me in chat it worked and gave 3 circles. The username E, I suppose 2.71828182845200459 in chat wants to see some math questions. So I think I'm going to move on. They actually just say yes, and I'm interpreting quite loosely what they want to see. So here's a math question. It is a transformation of the graph 2 to the x squared, which is not to be confused with 2 to the x squared, because that would be 2 to the 2x, which is not the same thing at all. 2 to the x squared is much worse, because if you put in a large number, this function on the left here says to square it first, even worse, and then do 2 to the power of x, which is much worse than merely doubling it before you do 2 to the power of it. So none of that. I just want 2 to the x squared. This question doesn't ask you to sketch the curve, of course. You might have had a go just to see what it looks like. I impression is the values are very large for most values of x. I guess if you put in 0, you're going to get the number 1. But that's not the question. The question wants us to talk about how that's related to 2 to the power of x squared minus 4x plus 3. Okay. If you've been looking at the screen for the last hour, remember to look away from the screen occasionally. Blink. Breathe. I'm going to drink some water. Over to you, chat. There's several options. I've got some of them on the screen there. That maybe you could describe the kind of transformations. What I'm more interested in is not exactly what the transformations are to get from 2 to the x squared to 2 to the x squared minus 4x plus 3. I'm interested in how you discovered it or how you approached checking these different options. Let's quickly have a look at them. So there's 5 on the page there. Some of them talking about reflections, some of them talking about translations and stretches, parallel to different axes, kind of all the transformations that you know about. How did you find it? How did you do stuff? Yeah, while I take my water break, I see Imo in chat tells me that Desmos breaks at about 50 circles, which is good homework. They've experimented with breaking Desmos. Good. Yes, there's a suggestion to complete the square. Yeah, when people in chat want to complete the square, but I want to try and get into your mind, right? How did you decide to complete the square? How did you decide that that was the right thing to do? You've got a quadratic there, and there are many things that you can do to a quadratic. Loads of things for those. Cuba says something which helps me get into their head. I think they say, wanted to do 2 translations at first, but didn't work. So I was looking at some sort of horizontal translation, which I think is very helpful. It's very honest to be able to say you tried something and it didn't work, so you backed up, tried something different, which is I think a really good skill to have as a mathematician. Good. So let's try trying some transformations. So if you do something like this, just as a translation, what would that actually look like? What would that actually look like? And maybe once you've written down this, maybe something clicks and you think, if these quadratics were the same, I'd be done, because that would be my translation. I mean, they're not, because this is sadly not going to match up, is it? But it's close. So I can see that a translation parallel to the x-axis is looking pretty good. Maybe with a equals 2, but I'm not going to commit. And then maybe you think about other transformations as well, until you find a combination that work together. Imo says that it's to do with the spacing in Desmos, and that breaks them. Yeah, Desmos is not great if you have fine detail, lots of different lines and not lines nearby. Aha! Suggestion that they factorise the quadratic first. This is a good idea as well. So this factorise the quadratic. You can do lots of things with this quadratic, can't you? And that tells you about what's going on as you get past 1 and 3, to do with those values being special. Those are the points where this thing is 1. So you could maybe think about the other graph and think about, does it repeat any values? We know how often this thing repeats values. I guess x equals 2 is probably the turning point, or the point where it starts going back up again. So yeah, good. Okay. And there's a suggestion in chat of how to do this, to multiply, and I've split it out like this, that it's also equal to law of powers 2 to the x squared, 2 to the minus 4x, 2 to the 3. This is an example of something that's true, but sadly not very helpful, because hey, we got this 2 to the x squared, that's brilliant. And we've got this 2 to the power of 3, we like that as well, because that just says multiply it up by 8. That's great. But then we've got this thing in here, which is a bit, don't really know what that means. Multiplying by 2 to the minus 4x is not one of the translations in my little list of transformations. Yeah. So I think 2 approaches then that people are suggesting that have worked for them are maybe trying completing the square just to see what happens, and discovering that it's this, and then doing some power laws. You see, I've got fewer terms to deal with now. So if I split this one up, then maybe I could get something like 2 to the x minus 2 squared, 2 to the minus 1. And by simplifying the quadratic first, completing the square as a way to simplify the quadratic, by simplifying the quadratic first, then I can get fewer terms in here, which are both happy, make me smile, because that one's a transformation to stretch by a factor of 1 over 2, and this one is a translation. I've still got to think about what order they're happening in, I think, but maybe it doesn't matter. Okay. Yeah, okay. And it seems like some people have approached that by completing the square in the quadratic, and some people have approached this by thinking about transformations to see what happens. You sort of wanted out of this to have a minus 4 in here, so you thought, I'll translate by 2 units, and then that doesn't quite work, but we can fix it by multiplying afterwards by 2 to the minus 1 to fix that thing at the end there. That number 3. So I really like this. I like that people are approaching this in different directions, which is really nice. Factorise the quadratic, then split it up. So splitting it is hard because of the powers. I did like factorising, but then I felt like I got a bit stuck because for me, I'm not quite sure what the next idea is. Maybe it's thinking about where the midpoint is for that quadratic and kind of symmetries of the graph. This original thing has definitely got a symmetry in the reflection in the y-axis, that if you replace x with minus x, then you get the same number back. This one seems to have something going on with the line x equals 2, which makes me think of transformations. But I think you do want some algebra in there as well. Okay. The username is the real Terence Tao, real fact checked, but I'm not sure they fact checked how to spell Terence Tao, so it's not the most convincing fake name I've ever seen. Oh dear. Remember, people in chat might be using their real names or might not be using their real names. There's no way to know. There's just no way to know. Oh, that's really made me smile, I'm sorry. Okay, here's another question from a math paper from 2017. I have modified it slightly. It was a multiple choice question, but I thought for you, trying out some past paper questions, I could just ask you to sketch minus f of minus x. There are some hints on the next page, but yeah. Someone in chat thinking about logarithms. That's very nice to see. So then they've got the quadratic, they've isolated the quadratic, and they can do operations on the quadratic separately. I like that kind of mechanic. Take a logarithm, put it up on jacks or something. Take the logarithm, have a go, mess around with it, and then put it back again at the end. Okay, new question. Here's f of x. The question wants us to sketch minus f of minus x. Do you think about what's happened after we've done some transformations? I mean, the question doesn't say transformations, but some transformations have clearly occurred. Okay. Terence with 2 R's. Yes, long questions are still going to be worth 15 marks for MAT 2024. Okay, so I think 2 things have happened here. Yeah. It doesn't actually matter what order you do them in. You can reflect in the x-axis first or reflect in the y-axis. Those operations, actually the order doesn't matter for those operations. Either way you end up with the same answer. It's quite hard to explain. Anyway, so what am I going to get? So this bit of the graph that comes in like this is going to get reflected to be like this to start off with. Maybe I should do this as a 2-step. I think I should do this in 2 steps. So I'm going to change my height. I'm going to do f of minus x first. So draw this like that. And then I'm supposed to draw minus f of minus x. But I think I would do it in 2 steps. And I'll try and do it correctly. Yep. So it's very negative, and then goes through, and then declines like that. This comes in, and whoop. Forgot it was supposed to blow up over here. Left a bit. There we go. I think something like this. So is this the same thing as just one simple transformation? Chat would like to know, is that just the same as doing one thing? Do people know what this is equal to? You can cheat, Andre says you can cheat by bringing a mirror. Still have to think about what you've drawn. This is not the same as reflecting in y equals x. the thing you actually get when you do a reflection followed by another reflection is that you get a rotation. That's a little bit hard to demonstrate, but I'm going to try with a bit of paper. So I have a bit of paper. I can do a reflection. It's not a real reflection, but it has kind of the same effect on the corners of this rectangle. If I reflect in the y-axis, I get this, and then if I reflect in the x-axis, I get this. And what you can now see is upside down writing, because the combined effect of those two reflections is a 180-degree rotation. Don't expect you to know that. Don't expect you to have ever tried this before, I think, but I guess you could try this at home. If you've got access to any rectangles, you could do a kind of reflection and then a reflection, and you end up with a rotation. It's an introduction, I suppose, to groups and symmetries, that the combination of a transformation followed by another transformation might itself be one simple transformation. Good, okay. Klein 4 group says hello. Good, yeah, 180-degree rotation. Very good. Okay, good. Chat are now excited that we've mentioned symmetry groups, which I think some people get to do symmetry groups in A-level, some people don't get to do symmetry groups in A-level, but do get to do them at university. So, good, right, okay. I've switched back into open day mode. Like, did you know that you can go reflecty, reflecty, and then it's all back. Reflecty, I can't do it with my hand. I haven't worked it out. Did you know you can go reflect, reflect, and then that's the same as doing a rotation? I worked it out. Reflect, reflect, and it's now upside down. I'm really pleased with myself. Right, okay. What are we doing? I'm also pleased that I got through this. The question with the most minus signs in. I might be safe now. Right, okay. Right, let's lose chat again from the screen. I really like this as a kind of example of doing some transformations. There's a kind of warm up there for some longer math questions. Okay, we've sped through those two short questions, having a look at transformation followed by another transformation. Yeah, I suppose I should probably ask what you think this graph is. If you had to guess, it's not really a game that you can really play for what's the function, but if you had to draw a version of that function in Desmos, you have to guess the equation, I don't really know what you'd pick. It's got to blow up at x equals 1, so maybe we want something like 1 over x minus 1, but it's not quite that, because it doesn't go to 0. Or something a bit different, not quite 1 over x minus 1. Then maybe you think a bit and it's like, well, it looks a bit like x squared near the origin. What does that mean? Goodness me. Maybe like x squared over x minus 1. Maybe add on a linear function, subtract a linear function, something like that. You don't want 1 over x out the front, because 1 over x would be enormous at 0. And this thing looks pretty chill at 0. It looks like it goes through the origin. It looks like it has a repeated root there, to be honest. Well, do I mean repeated root? Whatever. I think it might be. I had a look at the question source file. I think it might be this. When x is large, this is negative. I think it might be that. Just because, you know, well, then that's equal to, if you like, that's closely related to 1 over 1 minus x, but with some extra stuff going on. Yeah, something like that. It's sort of some sort of hyperbola, but not expected to know what a hyperbola is, or I've seen one before, or write down equations. I'm just playing with the thing in the question, just because, before I move on, because we did that so fast. Right, okay, time to move on. The worksheets on the MAT Livestream page come with some hints. The hints work, I think, quite well before you've seen the answer and are totally useless after you've seen the answer, so I'm going to skip past them. Next week, logarithms, the worksheet is already on the website. I've got a little bit ahead. The worksheet for logarithms is already up, if you want to see that one. Okay. Here's a longer question from 2008. It does ask about sketching. It also asks about integrals. I've put it here because it asks about transformations again. The question's kind of cute. It's got this idea that you'll take the function f of x. Let's copy this down here. f of x with what's clearly supposed to look like a repeated root over here at some positive value of x, going slightly down when x is 0. I actually quite like this as copy out the graph and think about what you're drawing as you copy it out. Seems to be forcing me to think about what I'm actually doing. And here are some plots in some order of y equals f of minus x, y equals f of x minus 1, and y equals minus f of x. And hopefully it's no challenge at all for you to piece together which transformation is which. We have 3 transformations you could do, which are reflections or translations, reflecting in different axes or moving things left and right, backwards and forwards. They involve minus signs, so I'm going to steer well clear of them, but you might like to think about what's going on here. Okay. Aha. Good. Yeah, should we do them left to right? So that first one, where it has a repeated root in about the same place, but everything's upside down, I think that's minus f of x. The next one, where all of the action is now happening for negative values of x. Well, not all of the action, but the repeated root is now happening for a negative value of x. That looks suspiciously like it might have been reflected in the y-axis, f of minus x. And then graph C, I think it's a translation because it looks very similar to the thing I've drawn. But now that graph is going through the origin. Almost called it a giraffe again. Not a mistake I make frequently, except today. Okay, here's a more interesting bit of sketching then, and it's more functions like the thing we just did in a short mat question as a warm-up. We're asked to sketch here 2 to the minus x squared. So this time I'd actually like you to think about the different values that this takes, depending on different values of x. And they've also got 2 to the 2x minus x squared. So if you were playing along before, watching the stream, thinking about transformations, I would like you to think about what transformation links these 2 graphs, so that even if you're not certain how to draw the one on the left, you might be certain how to draw the one on the right once you'd seen the one on the left. Over to you to think about how these things are related to each other. Also wants a stationary point, so we might like to think about points where this reaches a local maximum or a local minimum, points where it sort of takes an extreme value. Okay, but I'm going to look to chat for this, I think. Yeah, it's like e to the minus x squared, sure, because 2 is a bit like e. Oh gosh, we've got somebody with the username e in chat. I hope they don't mind saying that 2 is a bit like e. E is obviously much better than 2. Is it valid to switch to minus x squared plus 2x to the power and then use it as transformation of completion squared? Yeah, I think so. Yeah, so this is 2 to the minus x squared plus 2x, which you can then do some completing the square on, can't you? Yeah, I like that a lot. Carry on. Good. Keep that idea. So let me think about this one then. Somebody said it was like e to the minus x squared, which I suppose you might have seen. I assume the person who's saying that has seen, I don't know, the normal distribution or some sort of Gaussian thing. But even if you haven't seen one of those before, you know that when I put in x equals 0, I'm going to get the number 1. 2 to the 0 is 1. And if I put in a large value of x, well, this would be a very negative number. And 2 to the power of a very negative number is 0. Well, close to 0. So I'll put in something like this. Positive, but close to 0. And similarly, over here, this is symmetric. So in between, I suppose it's going to come up. Is this the maximum value that it could take? Pause. Well, minus x squared is negative. So this is 2 to the power of a negative number. So yeah, I think this is 1 over 2 to the x squared, where 2 to the x squared is going to be some sort of thing that's larger than 1, so this is dividing by something that's larger than 1, it's going to be less than 1. So I suppose that's my turning point then, that at 0, this has got the value 1, and that's a kind of local maximum, a turning point. Notice that although it said turning point, stationary point, I didn't have to do any calculus, I didn't have to differentiate it. Maybe if you're doing A-level maths and you've finished A-level maths already, maybe you know a way to differentiate 2 to the minus x squared, but either way, I think it's actually easier just to think about the values that it's taking to join the dots. Yeah, so the right is a scale. And somebody has mentioned Gaussian functions in chat. Hooray! I'm really pleased to see people finding links between other stuff that they've seen. It's nice to recognize them from different viewpoints, right? So yeah, this is literally a Gaussian function, probability bell curve shape. I have not drawn it very symmetric. Not my best work. Anyway, so people were, I think, completing the square over here. It's quite nice having lots of people doing different things. Frees me up to do all the same things as you're doing at one point, which means it's translated but also multiplied up. And I should think about the value when x is 0. Now, the value when x is 0 is also going to be 1, because if I put in 0, I could plug it in here and get -1 squared is 1, with a minus sign is -1, add 1 again, it's back to 0, or I could plug in x equals 0 over here. Once you've done an operation like this and you've got two equivalent expressions, it's your choice which one you work with for anything you want to do afterwards. Anyway, I think this looks like this. So taller, but still going through this point, and shifted to the right. Like that. Interesting. I suppose I could try and find other intersection points by saying, is 2 to the minus x squared equal to 2 to the 2x minus x squared? It sounds a bit silly, but I think I can start rearranging this, right? So I can multiply both sides by 2 to the x squared to get 1 equal to 2 to the 2x. Oh, this is definitely only going to happen when x is 0. There's only one point where they go through the same value. Are we supposed to find intersection points? No, but I've done it anyway. Okay, so sort of scale up and translate. Yeah, okay. So they're both going to 0, and this one's taller and larger values, but shifted, but it doesn't intersect. And over here, it's going to 0, somehow it stays below this line over here. There's no intersection point over here. I chickened out a bit because I didn't know if I should draw it intersecting or not. But now I've seen, oh no, I did some quick equations over here, and I've decided they don't intersect again. Question in chat: will it intersect at infinity? And that's a question that we're not really equipped to answer, right? What do you mean at infinity? So I guess maybe you mean if we made it all the way to infinity, both of them would have the value 0. Fair enough, I suppose. Does that count as an intersection point? Well, I'm not even sure it counts as a point, so I'm not gonna count it myself as an intersection point. But there are bits of maths where that's a really good idea for a way to something you should count as a point. The point at infinity is something people say sometimes. Okay, the last part of this question is about integrating this. I would quite like to skip this and maybe come back to it because I would like to talk about a different sketching and integration question. This one's fine. It's not terribly difficult, I think. I mean, it's an integral in terms of c, so I suppose maybe it actually is unfamiliar. I've got used to these of having a parameter that can change. Maybe I should talk about this a little bit. What do you think, chat? Oh yeah, I should have I look at chat. Chat's shouting at me that I forgot to label my stationary point, which has been shifted 1 unit to the right and 2 units up. So thank you, chat. X equals 2, where the y value is 2. One, 2. What's the value when x is 2? 1, 2. Chat's reminding me I should find the stationary value. I'd forgotten what transformations we did. We multiplied up by a factor of 2, and we shifted right by 1 unit. So this is 1, 2. And if I plug in 1, I do get the value 1, 2, take away 1 is 1, 2 to the power of 1 is 2. Good, okay, that does actually work. It is actually a point on the curve, not 2, 2, which I briefly had labelled there, which is not good. Okay, sorry, there are 2 people in chat telling me it's at x equals 2, and I'm afraid I think it's at x equals 1 because I think we've shifted right by 1. Okay. Thank you, Jack, for the reminder to do that. Why is that the transformation? Well, same reason as before, I think. We completed the square again over here. So we recognise that this quadratic looks totally different from the one we had before, but actually it's pretty similar. Minus x squared plus 2x. And then I did some factorisation in here. And I did this step quite quickly on the board, but that's because we've all completed the square quite a few times before, I guess. If I multiplied this out to check it, it would be x squared. There would be a minus 2x, but hey, minus sign out the front. So this is working so far. And minus 1, but then I've added 1 on the end as well to allow for that. So completing the square by checking as you go. Before I forgot to do this bit in there as well. We had just shown I of c on the board, this integral that depends on c. The thing we're supposed to imagine here is that I is some sort of function where you give me the number c as an input, and then I have some sort of complicated process, which is I have to work out y is like 2 to the minus x minus c squared. I have to work out that graph, and then I have to go and integrate that from 0 to 1 across some area. Maybe I have to go and sketch it for x minus c. This is all happening inside a box. Value. Okay, and then the value pops out of the box. That's the value. And in some sense, you can abstract this to say, well, this is just a function, right? You give me a number, you get an answer back. I would like to know what number should I put in the box to get a large output, which is something we ask you all the time, right? If this thing was just x cubed minus x or something, we say, hey, what's the locally best value to put in? What's the local maximum? And we do this sort of thing quite a lot. And the complication here is that you've got to understand the transformation that's going on and the fact that we're integrating. So if you like, the question is, we're going to integrate from 0 to 1. And we've got a function 2 to the minus x minus c, which is related to the things we were just talking about, in that it's a transformation of this graph, right or left. Oh, I've gone slightly off the bottom of the screen again, there we go. Transformation of this graph, left or right, and we'd like the area under that graph between 0 and 1 to be nice and large. Once you've had that idea, once you've thought about it, perhaps sliding backwards and forwards, or drawn yourself a couple of little diagrams to see what would happen as it slides sideways like this, I think it's pretty clear that what you want to do is keep moving right while this bit over here is smaller than the bit over here at 0. Keep moving right until those things are equal, until the value when x is 1 is equal to the value when x is 0, to match things up symmetrically. Not drawing a wonky line like that, that's terrible. Let's see if I can draw like that, there we go. Okay, so the area between the lines. You want, if the value over here is a bit larger, then you want to shuffle, you only get a bit more of that side of the pie. And if the value over here is too large, then you want to shift the graph right a bit to get a bit more of that. Sacrifice this bit over here to balance things out. I think I put x minus c. Oh, good question, Aussie in chat. Does it matter that we're squaring x minus c? No, in a way. Well, if we're not squaring, then it's got a totally different function, and actually I of c is very different if we're not squaring. But the square in here is allowed for in the fact that this is, well, I suppose, that graph by, and then x goes down like x minus c, transformed by something, some translation over here. The x squared is kind of part of this shape that I've drawn. The squaring part of this is part of the shape. That thing that we drew before, we thought carefully about x squared and how it was symmetric and went up and down. That squaring is now kind of baked in, so that if we do the transformation, that replaces the x with x minus c, and that's the thing that changes. The squaring is still there, it's still part of the expression, like the minus sign and the base of That was number 2 down there. If we weren't squaring, then the shape would be different. The shape would be something like 2 to the minus x would look like this. And then something kind of funny happens, that if the shape's like 2 to the minus x, which you could translate, then the correct answer is just translate right as far as you can, because look, the values go up and up. If you translate right, then the numbers get larger. So that one kind of doesn't have a satisfying answer for where you should put the graph. Okay. But crucially, just to reiterate it, and Ozzy has said that we've got there in chat, but crucially the squaring there is part of the function before I did the transformation. Okay. I'm not expected to calculate the maximum value because that involves those big tables of numbers that you see in A-level or equivalent. Okay, 6:30, perfect timing for another math question. In terms of my live stream schedule, you can do math questions whenever you like. I'm doing math question at 6:30. Okay, who's with me? Let's go. I've put this question on the Matt livestream because I did it with some people in real life, and we had a lot of trouble drawing x to the 1/2 and x to the 1/3. They were not sure whether x to the 1/3, well, they were not sure what this looked like at all. So I thought, okay, this seems to be good practice. I should put it on the Matt livestream. So I've added it to the playlist of things that we're talking about on that live stream. Yeah, okay. I think Desmos lets you do integration. If you want to go and find out what that value of IFC was, then you might like to go and do some integration. I think Desmos has the trapezium rule built in or something like that. So Syrup says inverse of x cubed, which is good, which maybe helps you draw it. You might like to think about its derivative. The particular thing that people asked me, well, I asked them to draw this graph and they asked me, oh, does that have 0 derivative or very sharp derivative when x is 0? That was something they weren't sure about, which I suppose you could check, couldn't you? You could work that out. We're just going to look for, we're just going to look over here where x is positive. I really like this question. So it defines lots of different functions all at once. I should have read the question, sorry. It wants us to sketch x to the 1/3. It asks us to sketch several things. They're calling them F1, F2, and F3. Where f1 is x to the 1/1, x2 is x to the 1/2, and f3 is x to the 1/3. Gosh, that's hard to say out loud. The point I'm trying to make is that each individual function is not that bad. Maybe it's a bit scary seeing f subscript k open bracket, which is the notation that you would use if you had a sequence of functions. If you had one function and then another one and then another one and another one, you might do it like this. What was the answer to the last question? It was c equals 1/2 to park that function right in the middle. I'll just show you what, there we go. Yep, I've got to say the number. Park it so that the transformation moves that maximum right to the middle. So c transformed by what half a unit to the right, just a half step to the right. It's linked to the ideas we were thinking about before, about how that transformation to the right moved the point in the middle, move the stationary value point. Okay, yeah, so finding the derivative is linked to the graph. Well, it depends what you want to do, but if you think, yeah, x to the 1/30 either looks like this or it looks like this, and I can't remember which one. It's one or the other. Then something that it might help you to check is to check the derivative. To check that the y with the x is 1/3 x to the minus 2/3, which, this thing is very large if x is close to 0. So this says, if x is very close to 0, then this thing gets enormous which is more like the blue curve than the pink curve. So I probably want to draw something a bit more like this blue curve rather than that pink curve. So maybe something like this. I suppose that helps if you can remember that it looks like one thing or another thing, which is the question these people wanted to ask me. If you already know what x1/3 looks like, then I suppose nothing can help you if you already know the answer. It's useful if you wanted to find some turning points. I suppose maybe you're not expecting this to have any turning points, so why bother differentiating? But I just want to make the point that you have the power to look for what's the gradient doing? How steep is the tangent, after all? It's the question that differentiating lets you answer. Okay, so there's one x⁻⁻. I'm supposed to draw 3 of these though, aren't I? So I should do y equals x, which I'm going to write like this, f1 of x. I think that's what they're doing in the question. And then I need to draw a couple more things. So, tricky question. I've got 2 more things to draw, and I think I'm going to draw them like this for the square root, and like this for the cube root. I think, but have I got those the right way around? Which one is larger than the other? And that's quite hard. I seem to have drawn this one going down again, which is not quite what I meant. I think I wanted all of them going up. Move this up a bit. All of these going up, but at different rates. So again, I'm thinking about the derivative there. I'm thinking about the rate of increase. I'm thinking about the way that if you put in a very large number, then x is huge, large number. The square root of x, not so big. The cube root of x, kind of tiny. So x is 10 to the 6. And I guess this is 10 to the 6. This is 10 cubed. This is 10 squared. So I think it's this way around. This is the cube root. But I've got them switching over as they go through x equals 1, because for small numbers it's the other way around, isn't it? If this is 10 to the minus 6, then this is tiny, 10 to the minus 6. The square root is like 10 to the minus 3, which is still quite large. And the cube root is like 10 to the minus 2, which is much bigger than 10 to the minus 3. So it's kind of the other way around. And of course everything is going through 1, comma 1. Right, I've labelled my picture with these 10 to the minus numbers, which I wouldn't do if I was actually sketching because then it gets very messy. I'm going to erase them. I'm just trying to illustrate what I'm thinking about how the different powers of different powers of things. Yeah, so it's different on the left of 1 versus the right of 1, which way around things are. Over here on the right, the more multiples of x you've got, the larger your number is. So x is big, x squared is huge, x to the 1/10, tiny. X to the 1/3, kind of in between. Whereas on the left, the more factors of x you've got, the smaller you are, because x is now a number that multiplied by x now makes your number smaller. That's the thing that's changed, I suppose, going left and right of 1. Whether multiplying by x makes your number larger or smaller. That's again, I think, a candidate for something that sounded clever in my head, and then I said it out loud, and it wasn't clever at all. Oh well, they can't all be winners. What are we doing? Not the extension, I'm looking at this. I'm sketching the graphs. Okay, I've done a pretty terrible job. Your picture is probably better than mine. Mine is really develops this kind of 10-degree rotation. Yeah, hello. So the method of finding, so there's a question in chat about finding roots, which I'm going to come back to in a second. So I've done the curve sketching, but the next part of this question asks about doing some integration to find some the area of some region. Where I just wanted to draw a particular diagram to help you out. Let's draw this. That's terrible axes. Let's go. There we go. That's a bit better. So if you've got 2 of these, like this, f of k and f of k plus 1, then something you could do is to imagine that the area in between is made up of the area under the top curve, to give you all of this large area, minus the area under the lower curve. So again, we're going to have to think really hard about which area is on top and which area is below. I think that between 0 and 1, the larger you make this number, the smaller the values are, because you're kind of multiplying by a little bit more x, not as much as a full factor of x, of course, to get from x to the 1/2 to x to the 1/3. You only have to multiply by x to the 1/6. Well, anyway, there's just a little bit more x in. What am I talking about? Exactly the wrong way around. What am I talking about? And I realised it by talking about it, which is good. It's because I drew a new picture and moved on, and erased all of my markings. Okay, k+1 on the top. We're going to have to think really carefully about that and get it right. To get to 1/2, from 1/2 to 1/3, you go to a smaller number. There's less x around. Good, okay, so I think I can integrate f of k+1 and f of k and do some difference between these. Good, okay. I'm going to give you a moment to have a go at that, if you haven't already. And I'm going to quickly read this thing in chat. Is the method of sketching x root via rotating the xy axis exclusive for x rooted, as there is a graph on the top left quadrant? That is not the case for x to the 1/3. So let's think. So they're asking about the relationships between the graph of y equals x squared and the graph of root x, where they are imagining this as a rotation of this left half of the graph. And that's confused them a bit when they've looked at x cubed and the graph cube root of x. Because, well, that's not what you get when you rotate the left part of this graph at all. The rule for inverse functions is actually slightly different. The rule for inverse functions is something like reflect in the line y equals x. And I know that's a more complicated idea, but to imagine a kind of line of mirror symmetry along the line y equals x and reflect, which is a complicated idea, isn't it? To kind of reflect like that in the line y equals x. Essentially, that switches all the x's and y's. It kind of moves the x-axis to where the y-axis was, and it moves the y-axis to where the x-axis was. And switching all the x's and y's is also how you write down the inverse function relationship. If instead of wanting y equals x squared, you want x to be y squared, so that you get the inverse. Now, for that to be a function, you might have to choose one of the roots, which is why we only draw square root x up here, rather than drawing the bit that's down here. Because square root x is defined to be the positive bit of this graph after you've done the reflection. Is it that? Let me think. So I've got this, and I go like that. Yep, it's this. Once again, having an L with your left hand, and then if you switch around, you get another L with your left hand, but now with your thumb pointing upwards, you've switched the x and y axes. You've done a reflection in that line in between, and you can feel it in your wrist, this diagonal line that goes between the two, that is staying fixed. That's the line that we're switching. And I know I'm doing a rotation with my hand, but it's turning over to show you that things are reflected. There's this weirdness about 3D rotations versus 2D reflections that let's not get into it. I can't actually reflect stuff in 3D. I can only rotate. I can only rotate my hands. The rectangle trick is actually just rotations. It's very annoying. Right. Okay, so the trick, the method that you're referring to in chat, to answer your question, the method that you're referring to is actually to take the right-hand side of the graph and turn it over by reflecting in the line y equals x. And that does work. That works really well for other roots. If you prefer, then you could take the left side, rotate it round, maybe do some reflections in the axes to get it in roughly the right place. And that works too. Good. Okay. Yes, so there's some suggestions coming through in chat about what the answer is for this, and people have been integrating, I'm sure, x to the something between 0 and 1, which you know how to do. It's x to the 1 over k plus 1 plus 1 divided by 1 over k plus 1 plus 1, the new roots, plug in 1 and 0, so I'll get 1 upstairs, which 1 to the power of anything is 1 over k plus 1 plus 1, which I can simplify a bit, I think, as k plus 1 over k plus 1 plus another 1. And then something very similar, if I put in k instead of k plus 1, I expect I would get k over k plus 1 just by, I'm not going to get away with this, am I? So for the other integral I'm supposed to do, integrating 1 over x to the 1 over k, I'm expecting to get k over k plus 1 because of the transformation where I change k plus 1 to k. I'm expecting that to be a transformation that we could apply to here and here and here, to just change this to k over k plus 1, which is some sort of translation, because this is the Graphs and Transformations live stream. Am I going to get away with that? Describing that as a transformation? I'm not sure I am going to get away with that. It's just saying, well, if you switch the k plus 1 to a k, then everything should work out, right? No, I don't think people are going to like that at all. I think maybe people would prefer it if I wrote let m be equal to k plus 1, and then maybe there'd be an m here, which is kind of almost what we want, and there'd be m over m plus 1 over here, which is kind of almost what we want. But maybe what people really want me to do is to integrate x to the 1 over k between 0 and 1, because that's what I just told you to do. And then maybe we could use these ideas about transformations and substitutions and replacements to say that when we get down to an answer at the end, which is multiplied to 1 by k, which is k, over, wait for it, k plus another 1. Oh, good, that worked out to be exactly what we thought it would be. But secretly, I think that is just a transformation, replacing k plus 1 with k, which I think might just be a translation. Right, okay, I think in the past when I've talked to people about this sort of thing, people have been very unhappy about transformations that aren't transformations of physical space, because you are thinking about these things in terms of graphs that you draw on physical paper, so people are thinking about them as physical transformations, but actually you can do a lot of things just algebraically, with transformations just changing your variables. Anyway, right, okay, I've got carried away with a bit of a different way of thinking about things. The question now wants us to do something else, so I'll scroll down. They bring in this line y equals c. Oh, what was the question actually asking me to do? Oh, the area is 1/6, so the difference between these things, which I like, is pretty simple. The difference between these things, if k is equal to 1, then I think I get 2 over 3 minus 1 over 2, which is 1/6, which is nice. Okay, I want the difference between these two numbers to find the difference between these two areas. Area under the top graph minus area under the lower graph. But yeah, somebody's got, wait, k is 1 or k is minus 4? Are they solving for k? Oh, if they solve the equation, are these things equal or not? No, I don't know. So someone in chat says, sad face, I got k equals 1 or k equals minus 4. I sort of don't even know why they've got k equals anything. Are they trying to solve for k? What were they solving? Anyway, okay. If that's the answer, what was the question? Game to play at home. So last part of this question asks another integration question. And I just want to talk about it because there's a nice way to do this with a transformation, which I don't think anybody would do, but it's maybe good life advice. As we wrap up with 10 minutes here on the stream, there's a question where you have, so is it square root and straight line, or is it it's f1 and f2, so it's square root and straight line. But we stop here. And we're asked to put the line y equals c, at such a point that these regions have the same area. I think we know that region is total area 1/6, so we could try and work out some expressions for the area of each of these, which is fair enough. And then Len in chat and Andre have each had an idea about a faster way to do this. So here's what I would do, is just probably to try and split these up, to try and talk about, if I want to find one of these areas between x and root x, then I might try and do clever things about splitting this up into maybe a bit of square root difference between square root and a line over here. Maybe square root curve from 0 up to, well, first they tell us to work out where this point is, but fine, whatever. Square root curve from naught up to c squared, and then subtract this triangle and add on this triangle to find the pink area. And I want the pink area to be equal to the blue area, or much better idea, I want the pink area to be 1/2 of the total area, which we already found. So you can use the previous parts of the question when you're doing a long math question, and here, rather than saying I've got to calculate both of these, I might calculate one or the other. Okay, there is a transformation that makes this easier to think about. So just here with 10 minutes left, before we do it this way with areas, if you do that reflection in the line y equals x that I was talking about just now, which is not an easy transformation to work with, really, then you get this picture. This is y equals x squared, and the question is to find a value of c such that this area on the left, after doing this transformation, is equal to this area on the right after this transformation. And this is easier because the limits are just more obvious. They're 0 and c for this thing over here, and the area is the difference between two curves, just x minus x squared, which is just a lot easier to work with. So somehow this transformation, flipping it around like this, is much easier to think about. But I don't think anybody really thought of this. I don't really know. This question is from quite a long time ago. I don't know if anybody tried this. Maybe I should find some students. I guess they would now be graduate students, see if they can remember. Did you think of flipping it around to reflect in the line y equals x? Is that something you'd ever seen before? Anyway, let's do the question the way that I think was intended, which is just to try and calculate areas. We did quite a bit of this last week as well, where we had some areas we wanted to find, and we thought about chopping them up and working out separate pieces. So here, the main thing I've done is to draw in this line to split this up into different regions, where what I want is, I've identified this point as being important because it's where the curve, reading left from right, is where we switch from having the region bounded between these two curves on top and bottom, which is something I can deal with, difference of two curves, we were doing that before. That all changes at this point here, where instead of being the difference between this curve and this line, after that the pink region is bounded totally different between horizontal line and that rising y equals x line. So this is the point of change, where once I've drawn that in, I can write down an integral like this. I want the integral from 0 up to c squared of root x minus x. That's for this first bit, this area over here, and then plus the integral from c squared, finish this off, to c, because this is c comma c, up to c of c minus x dx. I think I said I was going to subtract a triangle and add a triangle. That would have been much cleverer. I've gone for the difference between two curves. I regret that a bit. I'm going to be doing far too much work over here, when really I could just be, if I want the area of that pink triangle, I should just do c minus c squared over 2, right? Because it's a triangle with 45 degrees angles in it and stuff. I've written down an integral that's made this way too complicated. It's tricky, I suppose, to choose what you're going to do, switching between maybe parts of your brain that are good at geometry and trigonometry and spotting 45-degree angles and spotting isosceles triangles, versus the part of your brain that's just thinking it's just integration, we should just integrate, right? And you've got all of these different separate skills going on all at once, selecting what you're going to do. The Pythagorean theorem in chat has a pretty hot take. What if you differentiate everything and then integrate it until the highest power of x is x cubed? And then everything's unknown because you differentiate it. Making the answer E. It's not even a multiple choice question. The question is wrong, they say, which is quite a hot take. They've done some operations to a function that remove all of their understanding about what the function was. So now they don't know anything about the function. I don't know which question you're doing. Pythagorean theorem in chat. I don't know which question you're doing. Is it some sort of extension? No. I don't know what you're doing. But if you let me know what you're worried about, I can maybe help. I've got 5 minutes on the clock. Okay, either way, we've got some integration to do. We'll get some sort of equation involving C. And this turns into a polynomial question right at the end here. It's a really good question for combining topics together, because the condition for this to be equal to 1 over 12, or whatever it is that we want this to be equal to, the condition that's equal to half of the total area is some sort of equation for C. It's some sort of statement that rearranges quite nicely to 4c cubed minus 6c squared plus 1 equals 0. And then, brilliantly, the question says find C at the end. You've got an equation, let's go and solve it. Well, I can't see 0 doesn't work, 1 doesn't work. I don't know a formula for solving cubics. I know C has got to be somewhere between 0 and 1. So the next thing I tried was 1/2. And 1/2 works. A little bit of work to check that it works, I suppose. 4 over 8 minus 6 over 4. Oh, goodness me. That's a half minus 3 over 2. Oh, right, okay, so that's good then. Add the 1 and you get 0. Which is kind of surprising. As far as I can tell, it doesn't mean anything. But this question has C equals 1/2. The other question we did has C equals 1/2. But I think this time it's just a kind of coincidence. There's not a nice reason for it to be right in the middle that I can think of. It's not true in general, which is why the extension is here, because I wanted to know if this was true in general, and it's not. So I gave you this extension to go and check that in the general case. Oh, I can't scroll down there. In the general case, you get some other horrible equation, and I was going to ask you to solve it, but it doesn't have a nice solution, so I stopped there. That's the expression. Okay. Quick look at chat while we wrap up here. If you've got any questions about things that we've done, how have we used the fact that the area is equal on both sides? Good question. So I didn't tell you that I want this to be equal to 1/12, where that must come from the idea that overall this is 1/6. We found that in a previous part, and we would like the pink area to be equal to the blue area, which means it's half the area of this thing. So I want this to be 1/12, and that is where the +1 comes from in the equation. All of this multiplied by 12 gives you those factors of 4 and 6, those lovely flavours of C cubed come from the integrals on the left hand side, but yeah. Oh, and a question in a math question: if we can't get the final equation for whatever reason, but we can solve for C, we still get some marks. Yes. So separate instructions in the question, separate things you're told to do, and separate parts of the question are given marks separately, so that if you're doing sensible things, if you're making progress, so that maybe you can't do the first bit of this question, but you see that cubic and you think, I can find C, then you should get a mark for that. The questions are marked piece by piece. This year, the long questions are asking people to explain and justify their reasoning, which might be harder if you've just skipped into that part of the question. You might, I guess, is it 3? But the questions will ask you to explain and justify as well. So other things going on. Andre asks in chat, let's put this up on the screen as well, which math papers do I recommend? For the live stream, we're going to go back to 2007. The test before 2007 was quite different. It was taken in Oxford, for starters, by people who'd come to interview So it's taken by people a little bit later on and for a slightly different purpose in a way. I think the test was just a little bit different before 2007. So that's where I'm going to start for past paper questions. Those are the ones on the MAT website. If you're checking the website, the MAT website on the MAT page has got those ones back to 2007. I think you can find some that are a bit older, but they get sort of, in my opinion, a little bit weird before 2007. Nothing wrong with them, just not quite so closely related to what we're currently doing. Good, okay. What maths do you do in your free time? I'm currently trying to learn quantum theory, and I'm trying to learn a bit more about integration. I would really like to understand Galois theory more than I currently do. I had a go at that, but that's what maths I'm currently doing in my spare time. The 2007 papers. So I think the 2007 paper in particular is a little bit easy. 2008 also maybe a bit, but they're still good practice. If you can do the questions, then you can do the questions. If you get stuck on the questions, brilliant. That's exactly what you should be practicing to do maths of different things. Maths topic, do you recommend I do a 5-minute presentation in my school on cellular automata? One of them in particular, let me look it up for you. It's this one. I'll put the Wikipedia page on screen for you now. So rule 30 is a really simple cellular automata, so you can explain it really quickly. You can explain how it works. The Wikipedia page is lovely, and it's got this beautiful output that's just extraordinarily complicated and does lots of interesting things. 5-minute presentation, I think you should talk to them about rule 30. Was he the person who made a theory and was killed in a duel? No, me. No, not me. Who do we imagine? Galois. Yes, because I said Galois out loud. Yep. Has theory named after him. Did have a duel. Yeah, good. Change for MAT this year. We will see the new format beforehand because there will be a sample test on the MAT website very soon. It's been delayed very slightly because I made an embarrassing typo. Not an important one, just a spelling mistake. But I made a spelling mistake in a question, which has slightly delayed progress. We're trying to get it out this week. Hopefully next week on the MAT livestream, I will start by saying, hey, there is now a sample MAT paper on the MAT website for you to have a go at. And there's a question about whether multiple choice is easier or harder, and it really depends on the questions, I think. Okay. Really depends on the questions. Right, okay, I'm going to stop there. Thank you for watching the Oxford MAT livestream. We'll be back in 166 hours for another episode. Next time it's going to be on logarithms and powers. So I'll see you there to revise those topics and look at MAT questions on those things as well. As always, if you want to see the content in advance, I'm now a week ahead, so you can now do that at the MAT Live website at time of broadcast, which is me finally a week ahead of schedule. And if you have any questions, you can contact us via contact link there, or there's an email address in the YouTube description if you want a direct email address. Give me all of the power. Right, okay, good. Take care, everyone, and I will see you in a week. Have a nice evening. Take care, bye.